Hi class, this is a video on weak base equilibrium, which we covered on March 9th. So just a reminder of weak bases ionizing with water. So here's our methylamine base, and it gains a proton from the acid, and becomes this conjugate acid. The water loses a proton and becomes this conjugate base. Here are some examples of weak bases. So again, if we're going to write the reaction of pyridine with H2O, we want to take the weak base and ionize it in water. That will go into equilibrium. The base will take a proton from the water. Here's our base. Here's our acid. So this will become C5H5NH plus because it gains a H plus, and then OH minus left over, and because this is a base, it should form OH minus. Our first weak equilibrium example is calculating the pH for a 15 molar solution of NH3. So first you always want to write down the reaction. So take the weak base, ionizing it in water, writing down the equilibrium reaction. And then we want to write down our Kb expression, which will be NH4 plus over OH minus over the concentration of NH3. So now we want to set up our Rice table. Here we have our initial concentration, 15.0 molar. Water is a pure liquid and doesn't enter into the equilibrium expression. These are 0 to begin with, and then we can say this is minus x, plus x, plus x, 15.0 minus x, x, x. So then we can plug these equilibrium amounts right here into our Kb expression, and we know that Kb is equal to 1.8 times 10 to the minus fifth. So let's set up our equation here. 1.8 times 10 to the minus fifth is equal to x times x over 15.0 minus x. We can neglect x because the power of 10 for 15 is 10 to the 1. Here it's 10 to the minus 5. They're different by more than 3 orders of magnitude, so we can ignore that x right there and solve for x. And when we solve for x equals 0.0164 molar, and that's our OH minus concentration. Oh, I forgot my minus right here. So this is our OH minus. We need to find the pH, right? The minus log of the H plus. So what I can do is I can find a POH. That's minus log of 0.0164. And that's equal to 1.78. And then I can find my pH by taking 14 minus 1.78. And that will give me 12.21. All right, so let's take a look at the next example. Here we are given the pH, and now the question is to calculate the Kb. Okay, so we've got methylamine here. Methylamine has a formula of CH3NH2, and it will ionize with water. Again, we're going to write down our reaction. It's plus OH minus. Okay, and our Kb will be the methyl-amidium ion. Amidium, yeah, methyl-amidium over our methyl-ammonium. All right, so what we can do is this pH of the solution, remember, this is going to give us the H3O plus at equilibrium. Okay, so that's our H3O plus at equilibrium. If we take a look at this Rice table here, our initial concentration is 1.0 molar. right? We're going to have exactly the same sort of setup, minus x, x, plus x, plus x, 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 right? And if we can find our OH minus concentration, that's x. Okay, so we have our H3O plus at equilibrium, right? We have our pH at equilibrium. So we know that our pH is equal to 12.32. So our pOH is equal to 14 minus 12.32. And that will give us a pOH of 1.68. So from that, I can find my OH minus concentration. That's going to be 10 to the minus 1.68. That will give me a OH minus concentration of 0.0209 molar. So I now know what X is, right? This is equal to X. So I can plug in now for X into my KB, right? My KB is going to be equal to X times X over 1.0 minus X. So now I can just take this number, plug it into here. So that's 0.209 squared over 1.0 minus 0.209. And when I solve for this, I end up with 4.5 times 10 to the minus 4 for my KB. So then we talked about polyprotic acids. Okay, so polyprotic acids have more than one acidic proton, so things like H2SO4, H3C6H5O7, that's citric acid. And as you pull off protons on polyprotic acids, it gets harder and harder to pull off protons. So here we have an example of a polyprotic acid, phosphoric acid. So you can see that the hydrogens get transferred, but the Kas, if you look, the first one is 10 to the minus 3, but then they get, that got cut off over there. They get increasingly smaller as we pull off protons because it gets harder and harder to ionize. And the general rule is that if your Ka2 is 3 orders of magnitude different from your Ka1, we can basically neglect the amount of H plus from here. Same with this one, right? These all can be neglected, and we can base our pH off of just the first Ka1. The only one where we cannot neglect this is sulfuric acid. Okay, sulfuric acid, this is strong enough that it's going to make a difference. Okay, can't neglect Ka2. Okay, so that you have to calculate how much H3O plus comes from this and add it on to what you get from the first first proton being taken off, the first ionization. All right, so for this pH of a polyprotic acid solution, if we look at the two Kas for carbonic acid, these are the Kas for the first proton being removed for carbonic acid and then the second proton being removed for carbonic acid. We can see that the difference between those is more than 3 orders of magnitude. So we can neglect, okay, that one. We can base our pH on just the first ionization. So here we have H2CO3 goes into equilibrium and forms acid. We have HCO3 minus left. And so we do not need to worry about the ionization of this species that's formed. We can just base our pH off of just this reaction. So our initial concentration here is 0.0037 molar. Okay, so then our usual Rice table technique. Minus x, 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 and then we can put this into our Ka expression. Ka1 is going to be H3O plus over H CO3 minus over H2CO3. Okay, so then we're going to get x squared over 0.0037 minus x, and that's going to equal our Ka1 over here, so 4.3 times 10 to the minus 7. And so we can solve for, we can neglect x here. It's more than 3 orders of magnitude different. So x turns out to be our, let's see, where is it? 4.0 times 10 to the minus 5. And that's our H30 plus. So our pH is equal to 4.40, the minus log of this. All right. So the last part was to get the relationship between Ka and Kb. And Ka and Kb, these are for conjugate acid-base pairs. And that will equal Kw, which is 1 times 10 to the minus 14. So if you take a look here, right, we have Ka and we have Kb over here. These are related by 1 times 10 to the minus 4. If you multiply these together, you get 1 times 10 to the minus 4. There's a derivation in your textbook on these pages if you want to take a look at that. But you can see that for a very strong acid like HNO3, the conjugate base NO3 minus has basically no basicity. It is pathetic, okay? We just call these pathetic ions that can't do any acid-base reaction in water, right? They don't want to go back to this acid because it's so strong, it will just completely dissociate. But for a weak acid like HF, right, which has an equilibrium constant, its conjugate base also has an equilibrium constant. And the stronger the weak acid, okay, the stronger the acid, the weaker the conjugate base. Okay, you can see that the relationship between the two, right? The stronger the higher the Ka, the lower the Kb, which means stronger the acid, the weaker the conjugate base. So here, if we want to calculate for the base dissociation constant Kb for F minus, we need the Ka for HF. We need the Ka for the acid, and then we can calculate Kb for F minus. So here, Ka, right? Remember the relationship is Ka times Kb equals Kw, which is 1 times 10 to the minus 14. And so if we know what Ka is, right, we can see that Kb is equal to Kw over Ka. So that's 1 times 10 to the minus 14 over 6.8 times 10 to the minus 4. Okay, so then we, when we calculate this, we will get 1.47. Okay, I guess we should round that to 1.5 times 10 to the minus 11. Okay, for our Kb. And this one is done the same way. Okay, again here, Ka times Kb is equal to Kw. So in this case, we're looking for the Ka. So Ka is equal to Kw over Kb. So plugging those numbers in. We end up with 5.6 times 10 to the minus 10. And so why do we need to know how to do this? Well, the next lesson, the next part of our acid-base journey is to find the pH of salt solutions. And so in order to do this, we need to be able to use the conjugate acid or the conjugate base equilibrium in order to calculate the pH of a solution when you put a salt in. And we can only get the conjugate acid Ka or the conjugate base KB by using this relationship.